Hello, my name is Max Trigub, and this is my Physics Lab 5. So, for this lab, I was asked to create a custom example of physics principles. So I chose a three-point shot as a perfect representation of projectile motion. In this representation, I performed this lab to observe how time, velocity, and force are interrelated within a closed system, and I effectively recreated projectile motion within GlowScript, and as such I recreated its associated physical properties. And this was possible due to my utilization of Newton's second law of motion. For those of you that don't know what a three-point shot is, this is a three-point shot. It is taken from behind the three-point line, which you can see on the court, demarcated with the black line, and it is towards the basketball hoop because that's what you shoot towards in basketball. In this lab, I assume that Newton's second law of motion applies to three-point shots, as it does to everything else. There are no outside forces acting upon the basketball hoop system. The basketball acts similarly outside of the 2-second time frame, and that all measurements are accurate. For my procedure, I modeled projectile motion in GlowScript, which included modeling the physics equation, the sum of all forces equaling mass times acceleration in GlowScript, and also modeling the velocity after the velocity update formula, which is velocity equals initial velocity plus acceleration times time, and also making sure that all of my physical values were in agreement with the formula distance equals initial distance plus initial velocity times time plus 1/2 of acceleration times time squared. I then inputted known physical values concerning basketball courts into a projectile motion simulation, which includes the distance from the basketball three-point line to the hoop, which is 23.75 feet, and the distance from the ground to the hoop, which is 10 feet, as well as the mass of the basketball, which is around 0.615 kilograms. I then used known values to compute total time, after which I compared my experimental value of time with actual three-point shot time spans, which vary from around 1 second to 2.5 seconds, and then I updated my work based on any errors. These are the states of my basketball three-point animation in GlowScript. As you can see on the left, it's the initial state with the orange circle representing the ball, the basketball, and the red hoop representing the basketball hoop. And on the right, the trajectory of the basketball through the basketball hoop, as well as the origin, which is represented by the yellow circle. Here are my graphs associated with my basketball animation that I got using my code. It's just a bunch of graphs of position in the x direction over time, position in the y direction over time, velocity in the x direction over time, and velocity in the y direction over time, as well as the trajectory of the object. And it's very important to note that the velocity of the ball in the x direction over time is constant, which reflects the derivative of the position in the x direction, and the velocity in the y direction over time is linear but not constant, which reflects the derivative of the position in the y direction over time graph. What I discovered from my lab is that with no outside forces present, the basketball hoop system mimics Newton's second law of motion, which states that the sum of forces is equal to mass times acceleration. This is because the basketball hoop system is a realistic physical system that perfectly represents projectile motion, and projectile motion is representative of Newton's second law of motion because it relies on the sum of forces being equal to mass times acceleration. Also, the total time is equal to the horizontal distance divided by horizontal velocity, and that's how you can derive total time for projectile motion. And the graph of y position over time is quadratic, while the graph of x position over time is linear.